Hey guys, Miss Peterson here. So, what we got going on today is we're going to be talking about concentration. We're going to learn how to calculate concentration in a couple different ways, and we'll also learn about the factors affecting concentration. This is chapter 13 of your Brown LeMay textbook, and then we'll also do some more practice with it. So, whenever we're talking about concentration, all we're talking is the amount of solute, which is the thing that dissolves in solution. So think of the amount of sugar in your Kool-Aid, the amount of food coloring in your Gatorade. Anything like that is a measure of concentration. The most common one that is used all the time is molarity. Okay, so molarity is the moles per liter. We're going to write our equations over in these boxes. So molarity you can think of as your moles of solute over your liters of solution. Okay. And we use a capital M for it, or you can use moles per liter. You'll see it both ways. They mean the exact same thing. Another common way that you'll see this a lot on like drinks or on like household cleaners, is percentages. So just like any percentage, it can be anything. It could be a mass percent, it could be a volume percent, or sometimes they might even ask you a mass or volume percent. But no matter what, it's the part that is your solute, the one that you're looking at, over the total, and then you times it by 100 to get it in percent form. So since it's a percent, there are no units. And again, just look at the problem. If they're asking you for mass, it's mass over mass. If they're asking you for volume, volume solute over volume of solution. If they're asking you mass to volume, the mass of your solute over the total volume of your solution. Okay, cool. Another one you'll see on occasion, this is used a lot in like pollution or things like that, it's parts per million or billion. It's still mass problem, so it's still the mass of your solute over the total mass of solution, but instead of making it a percent, you're going to make it per million or per billion. So mass of solute over the total mass of your solution, and then you times it by 10 to the 6th for parts per million, or 10 to the 9th for parts per billion, just depending on what they're asking you for. And it's written as ppm or ppb for parts per billion. Okay. Another one you'll see on occasion is a mole fraction. We've already done this for gases, but you can use it here too. Like it's saying, it's the ratio of the moles. So it is your moles of solute over your moles of solution. Okay, solution. Okay, moles solute over total moles. And then some other one that you'll see, not as often, but you might see molality. Molality is used because it doesn't change with temperature, where a lot of the other concentrations will. But molality is moles of solute over kilogram, not of total solution, but kilogram of the solvent. Again, you don't really need to memorize this one, just know what it represents in case it comes up. And while this seems like a lot of calculations, all you need to be able to do is solve them by their units. Okay, so as long as you make sure that your units are right and you know the units for molarity and such, you'll be fine. Also, in solution, you'll often have to use the molar mass. So don't forget, you can always use molar mass to convert grams to moles. And you can use the density. Density, if it's given to you, can convert from grams to milliliters. Some other conversions that will be helpful that you need to have memorized is that there's 1,000 milliliters in a liter. Sometimes you'll see micrograms or microliters. Those are 10 to the 6th. So 1 microgram is 1 times 10 to the negative 6 grams. That might come up. Another one is that there's 1,000 grams in a kilogram. Okay, cool. For now, just to keep this video a little bit shorter, I'm going to go ahead and skip the solution calculation examples. I'll be posting another video going over those. But let's skip ahead to the factors affecting solubility. Okay, so what factors affect the concentration, or what factors affect how much will dissolve? First, you need to know if something will dissolve. So when thinking about whether or not something will dissolve, always remember like dissolves like. In other words, polar or ionic substances are more soluble in polar compounds, where nonpolar substances are more soluble in polar solvents, or in nonpolar solvents. So things that are polar will dissolve in water, because water is polar. But things that are nonpolar, like oil, won't dissolve in water, because the nonpolar thing won't dissolve and mix in a polar thing. Just because of their intermolecular forces, they don't interact with each other, so they tend to stay separate. Some other things that could affect the concentration is the pressure. So pressure always going to be more important for gases. Okay? The solubility of a gas increases under increased pressure, which makes sense. Okay? If there are more molecules moving around and more molecules hit in the water, more of them are going to mix with the water. Okay? So more pressure means there's going to be more gas. This will come up again a little later. But pressure has very little impact on solid or liquid solutes. They're like, what's going on up there in the gas? Oh yeah, we don't care. Okay. Temperature is an interesting one. So in general, we know that when you heat something up, you can get more to dissolve. So it usually increases with increasing temperature. Normally, if you heat it up, you can get more salt to dissolve, more sugar to dissolve. That's how you make things like caramel, is you heat it up so that the sugar will dissolve in the water. However, gases are the opposite. Okay? When you heat up a gas, the molecules are moving more. Okay? So the solubility of a gas in water always decreases with increasing temperature. And that's what you can see in this graph over here. You can see nitrogen, its solubility of it, is decreasing as the temperature increases. This is a really big problem with global warming because temperature of Earth is increasing, which is actually decreasing the amount of oxygen in the oceans. So it's harming some marine animals. So let's think about these things and talk about some examples. I talked about pressure. So why does a soda can fizz when you open it? Okay, you guys have done that before. So if you have a soda can, it is under pressure, okay? It's pressurized in there. And when you pop open the cap, it changes that pressure. It lowers the pressure. When you lower that pressure, not as much gas can be dissolved in that soda. So the gas undissolves. It bubbles out. Okay? So, like I said, when it's in the sealed can, it has a high pressure or a higher pressure, which means the gas that's in soda is carbon dioxide, so more carbon dioxide dissolved. When you open it, the pressure decreases, okay? Pressure decreases, which means less CO2 dissolved, aka it bubbles out. It undissolves. Okay, let's look at another example. It says to arrange the following substances in order of increasing solubility in water. Okay, so water is polar. Water is polar, water is polar, water is polar. So the things that are going to dissolve in water are going to be the ones that interact with that water the most. So if you look at A is a totally non-polar molecule. It's only carbon and hydrogen. So A is non-polar. That means it is not going to dissolve. We can already tell you that that's going to be the least soluble. Okay, now let's look at the rest of them. This one has an OH group, this one has two OH groups, and then this one has that chlorine. So all three of these are going to be pretty polar molecules. Also, we have to think about those intermolecular forces. Water likes to form hydrogen bonds, so if it's with something else that can also form hydrogen bonds, it's going to be better able to dissolve that because it's going to have a lot of interactions that can go on. So if you look at C, C has two of these groups that could dissolve, or that could interact with water through hydrogen bonding. So it is going to be the most soluble compound. Okay, now we're left with B and D. B has that OH group that has hydrogen bonds because, you know, it's fun, where chlorine isn't quite. While chlorine is polar and it's going to have a dipole moment toward that chlorine, it's not hydrogen bonding, so that interaction with the water is going to be a little bit weaker. So D is going to be weaker than B. So therefore, more B, more interaction with water, means it's going to be better able to dissolve. Okay, so A is the worst because it's nonpolar. C is the most because of all those hydrogen bonds it can form. B can also form some hydrogen bonds, so it'll be pretty soluble. D will be soluble, but not quite as soluble as the rest of them. Okay, and last but not least example. Predict whether each of the following substances, I'm going to move that up, is more likely to dissolve in the nonpolar solvent carbon tetrachloride or in water. Okay, so we have to remember like dissolves like. C7H6, that is nonpolar. So it will dissolve better in the nonpolar solvent, CCl4. Na2SO4, well, that one's ionic, okay? And ionic substances dissolve much better in water. HCl is also a very polar molecule. It's actually an acid, superpolar. Loves to dissolve in water. And then we have I2. Well, each of those iodines is going to pull electrons equally. So I2 is going to be nonpolar. Okay, so it will dissolve better in the CCl4. Okay, just using that whole idea of like dissolves like. Okay, cool? Okay, cool.